Welcome back everyone. Let us start with lecture 3. So we were discussing symmetry elements and symmetry operations, and in that let us continue our discussion on proper axis and proper rotation. We have seen an example of water molecule and coordinate system, how C2 axis or C2 rotation affects water and Cartesian system, right? So let us continue with that, and let's take few more examples so that this is very clear. So let's take an example of a molecule called BF3. Yes, the configuration is trigonal planar molecule. So trigonal planar. Let us try to list down what all symmetry axes are present in this. So let us first try to identify the first symmetry element or the proper axis. So this will be perpendicular to the plane of the board passing through B. So this is called as C3 proper axis, right? And then we will see what all operations it will give. Another axis will be the one which is actually in the plane of the board and is passing through B and F atoms. So this will be called as C2 axis. C2 axis. And how many such C2 axes will be present? There will be 3 such C2 axes present. So we have 3 such BF atoms. So we'll have this C2 and another one passing through this, right? So 3 such C2 axes. Now let us see what is the effect of C3 and C2 operations onto this molecule. So let's say if we draw this again quickly, B, F, F, F. So you have 1, 2, 3. Now we can do C3 operation M times, right? Cn operation M times. So N is equal to 3 over here and M is equal to 1. So if we do that, we will do a 120 degree anti-clockwise rotation because this is 2 pi by N, right? So what do we get over here? B, F, F, F. Now this one comes here, 2 goes there, 3 goes there, right? So we have 1, 2 and 3. Now let's say similarly if we do C3 operation twice, what do we get? So instead of 120 degree rotation, we have to do now a 240 degree rotation because 120 is C3-1. So C3-2 will be 240 degree rotation. So what do we get? B, F, F, F. So again, this is rotation will be anti-clockwise, but now 1 actually moves all the way here. 3 moves all the way here and 2 moves all the way there, right? So we have 240 degree rotation. So 1 comes over here, 3 over here, 2 over here, right? This is C3 done twice. Now you can see that if you do C3-1 over here, this is also related by C3-1. So if you do C3-1, 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 it actually gives rise to C3-2, right? So you can see that result by yourself. So C3-1, C3-1 gives rise to C3-2. Okay. So that's all C3. If you do C3 thrice, what do you get? So let's say you also do C3 3 times. So 3 times means 360 degree rotation. So 360 degree rotation is 0 rotation, right? So you get your molecule in identical configuration instead of equivalent. So these two are equivalent configurations. So this is equivalent, this is equivalent. Now what you are going to get here is if you do C3 3 rotation and equivalent identical configuration. So this, let me write down, is called as identical configuration, because the atoms are actually not moving from their place. Okay, and for this reason this is also called as identity operation, because you have not actually done any movement. So C33 is actually equivalent to identity operation, right? So let's look at further. Let's try to do a C2 operation now on this molecule. So our first C2 will be in the plane of the board, passing through these atoms. So if we have 1, 2, 3. Now remember, anything which is lying on the symmetry element does not move, right? So C2, which is passing through BF1. Okay. This is just to identify which C2 we are using. Now if B and F1 are not moving, the only atoms that will move are F2 and F3. So this will be 3, this will be 2, because now 2 has actually moved this side and 3 has moved this side, right? So F3 is replaced by F2. Okay. Now similarly we can keep on doing other operations. So if we continue with C2 BF1 again, we will see that we will get, so I'm not moving a BF1. So what should we write here? So this will be 2 now, and this will be 3 over here, right? Because again F3 will go to F2, F2 will go to F3. Now if you see this, if you want to go from directly from here to here, so C2 done twice will be actually identity operation, right? So identity, or you can say C2 done twice. So C2 done twice will give you identity operation. Okay. So now let's also see what is order of the axis. N. So it's defined by N. So it's the largest rotation. So we can say largest value of N such that rotation by 2 pi by N gives rise to equivalent configuration, right? So this is called as order of the axis. So for example, this is proper axis with an order 2. The previous one which we saw was proper axis with order 3. Now if a molecule has more than one proper axis of rotations, axis with highest order is called as principal axis. Principal axis of rotation. So in case of BF3, C3 is principal axis. Right. So let's see more examples. So let's go to square planar XEF4. So what all axes it will have? So it will have let's say one axis which is perpendicular to the plane of the board. So this is perpendicular to the plane. Also this is a square planar. So which is perpendicular to the plane of the board. This will be a C4 axis, right? Collinear to C4, there would also be a C2 axis. Okay, so we will try to work it out. Now, in addition to that, if you see, there would be one C2 axis which is actually passing through FXEF bond, right? So this will be C2 prime, and there will be two such axes because there are two such stretches. So there will be one more like this. So we can write down over here 2C2 prime, right? Then there would be another C2 which is actually bisecting the XEFXE angle, right? Instead of passing through the bonds, now it is bisecting this angle. So XEF, this is also a C2. So this will be called as C2 double prime. This is just to identify or distinguish between different C2s, and there will be two such C2 primes, right? So these are all the proper rotation axes which are present in this molecule, and C4 will be called as principal axis, right? Because this is the axis with highest order. Okay, now how many rotations each axis will give rise to? So let's try to work it out that as well. So C4 can give rise to C4 1, C4 done twice, C4 done thrice, C4 done 4 times, right? So if you do C4 done 5 times, this will be equivalent to C4 done once. Okay. If you go to C4 done 6 times, this will be equivalent to C4 done twice. So it keeps on getting repeated. Okay. So now let's actually try to work out all these operations and see for yourself. So XE, F, 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 1, 2, 3, 4. Okay, let's quickly do C4 1. Okay, what do we get? XE, F, 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 F. So this is a rotation by 90 degrees, C4 1, 2 pi by 4, right? So this is 2 pi by 4 rotation, which is 90 degree. So 90 degree anti-clockwise, 1 will come over here, 2, 3, 4, right? Now let's do C4 2. So C4 twice will be 90 degree plus 90 degree, right? So that will be 180 degree rotation. So 180 means that now 1 will go to its diagonally opposite position, 1, 2 will go there, 2, 3, 4. So again, let's do C4 3 operation. So now 3 operation means the angle will be 90 into 3. So that is, tell me, this is 270 degree. So now 1 moves all the way to this position. 2 moves all the way to this position. 3 and 4. And now similarly, if we do C4 4, the rotation is 4 times. So 90 degree into 4, that is 360 degree. That means no rotation. So you get the original molecule back over here, right? So these are called as equivalent configurations. This one would be identical configurations. So that's why, so C4 1, 4 operations it will give rise to, C4 3, and C4 4, which will be equivalent to identity, right? Now, if you keep on going further, C4 5, again you will go back to C4 1. So C4 5 will be 90 degree into 5, that is 360 plus 90. So 360 is cancelled out. So this will be equal to C4 1 operation, right? So that is very straightforward to see. So therefore we can now say that rotation by 2 pi by n carried out successively by m times gives Cnm, and if n is equal to m, we get Cnn, which is equivalent to identity. And in this way, if we keep on going, if we have n plus 1, this is equal to Cn. If it is n plus 2, it is equivalent to Cn2, and so on. Okay. So thus we can say a proper axis of order n generates n operations. So we will see later that why number of operations are important. So it's in the definition of mathematical groups that we are going to learn later. So we need to understand that what are the proper axes of rotations present in a molecule and how many operations it will generate. Okay, so this is a symmetry element and this is a symmetry operations. So we need to know both. We need to first list down all the symmetry elements or all the proper axes of rotation for now, and what are the symmetry operations or how many operations it will generate. So let's take one more example to list down the symmetry or the proper axis of rotation. It's a simple benzene molecule, H. So I'm giving you an answer. Try to verify the list of proper axis of rotation. So there will be one C6, and also try to work out what all operations it will generate. Then you will have C3, you will have C2. These three are collinear to each other. Then you will have C2 prime, three such C2s, and 3 C2 double primes. Okay, so try to identify where these are, and let's also find out if there is any C4 present, if there is any C5 present in this. Okay, and then what are the corresponding operations it will generate. So for example, now this should generate 6 operations, this one should generate 3 operations, 2 operations each, right? So take it as a home exercise and complete this. Try to locate these axes onto the molecule and try to generate all the operations, corresponding operations. Okay. So another important point is, if you want to draw the molecule onto the Cartesian system, so a note on axis definition in Cartesian coordinate system. So you can say that while imposing So sometimes it is required in this course while imposing a set of Cartesian axes on a molecule z-axis lies along the principal axis of rotation. So you can say that if you don't know where the principal axis is, you will put the molecule incorrectly in the Cartesian coordinate system, because if you're not putting z-axis along the principal axis, you might not get correct results for the problems, right? Then x-axis lies on to the molecular plane. Of course, it has to be perpendicular to z-axis or the principal axis. So we can also say or in the plane containing highest number of atoms in the molecule if molecule is non-planar. So let's say if we want to put our BF3 into Cartesian system, how do we do that? So this is the right-handed coordinate system, x, y, and z. So of course, if you have defined z and x-axis positions, the y-axis is determined automatically by right-handed coordinate system, right? So if we are keeping our molecule or the B, so we have to put it such that the C3 axis, which is the principal axis, lies along the z-axis, right? So we will put B, F, F, F. So this BF3 molecular plane is now in XY plane. X-axis is along one of the BF bonds, right? And z-axis is along the C3 axis. Okay, so this z-axis becomes our C3 axis. X-axis is now one of the C2 axis, and then these two F's or these two fluorine atoms would lie onto the XY plane. So that's how you try to orient the molecule onto the Cartesian coordinate system. Okay. Let's take one more example before we stop. So let's try to work out C2H4 where all the axes will be present in this. So C2H4 will be, if you draw out the structure, it will be like this. It's a planar molecule again. Right? Okay. So let's try to draw what all proper axes of rotations will be present in this. So one of them is very clear. It's passing through the CC bond, C2. Another is bisecting the CC double bond. And the third one is actually perpendicular to the plane of the board and through this bond, right? So it will be like, I'm drawing it like this. which is actually perpendicular to the surface. So this is third C2 axis. So there will be 3 C2s. All 3 will be perpendicular to each other. Now your exercise is try to identify principal axis and put this molecule on Cartesian system. Okay, so try to do this at home. Also, let me give you a few examples to work at home. So let's try to do CH4, then C2H4 you're going to do. Then I have also given you C6H6 benzene. Let's also try to do C6H12, both the forms, boat and chair, so cyclohexane, both the forms, and try to see what all list down proper axis of rotations, and then find the principal axis and put the molecule on the Cartesian system. See if you can do it. So I think that is all for today. So let's continue our discussion on symmetry elements and operations, and we'll start with symmetry planes. That's all for today.